Welcome back to Anatomy. My apologies again for this being so delayed. I can't seem to get a break. Better late than never, I suppose. I do apologize. I feel very bad for not being able to be as available as I would like to be, but I guess we're all just doing the best that we can do. So moving on, we are diving into the skeletal system, and so I want to give you a nice introduction into basically how to organize the skeleton of the body, of the human body. And so moving forward, this actually, coincidentally, this front picture is actually going to be kind of helpful for getting you to grips with where stuff is located. A lot of introductory anatomy is, in my opinion, is just getting to grips with sort of the landscape of the human body, you know, whether it's muscles, whether it's bones or other structures. Knowing where things are, I think, is a good first step in making bigger connections later down the road. So continue to keep that in mind and continue to obsess over where and what regarding the human body. So without further ado, let's move on. Like any other system, as we dive into the skeletal system, we're going to observe some very discrete functions, of which there are basically 5 big ones. Just like any other system, you can find more minute things that it's responsible for, but these are the big 5 that are easily identifiable and commonly cited. And so without further ado, here are the different functions of the skeletal system. Number 1 of 5 is support. The skeletal system lends support to an otherwise very squidgy and non-very productive just bag of meat. Mobility is a huge thing in living organisms, and when you get to a certain size, you have to start putting in some sort of scaffolding so that it has some substance, something to support the being as a whole. And so in our case as humans, we have a skeleton. And that skeleton acts as the supports for your muscles and the other bits of your body to attach to in sort of this larger framework. And bones are responsible for protecting many of your organs. If you think of your trunk, your thoracic cavity is largely protected by your ribs. It's a lot better to break a rib than to pop a spleen or to, tear a kidney or something like that. And so they offer protection in a number of ways, not just in your thoracic cavity. Along with support comes movement. And this might seem intuitive, but if you didn't have your skeleton, your muscles would be attempting to only act on the rest of your squidgy self. And so your skeleton being there allows significant leverage to be produced. Strongest of your muscles would be your jaw, your masseter muscle, which attaches to your mandible. So the 4th and 5th functions that your skeleton system is responsible for take place inside some of your bones, and the first one is storage. And so a whole host of minerals, namely calcium, as well as a host of other sort of ingredients that your body uses, like lipids, are stored in the yellow marrow inside your bones, whereas the red marrow inside your bones is responsible for something called hematopoiesis, which is basically develops or gives rise to the hematocrit or red blood cells inside for your body. Notably different than erythropoiesis, which is responsible for strictly just making blood cells. Hematopoiesis is actually responsible for making all of your blood plasma, all the ingredients that go into your blood, not just the individual red blood cells. That is a nuanced but important distinction. And FYI, some of you with a robust culinary culture probably will have cooked with marrow bones at some point in your life, because they are phenomenal at elevating your cooking, especially when it comes to soups and stews. And my dog is an absolute fanatic over a good marrow bone. So just as a little sidebar, marrow is a great piece to a lot of cultures' culinary endeavors. But now we actually get on to the classification of bones. How would you sort all the bones in the human body if you were to take apart a skeleton and basically put the bones into different piles? You essentially wind up with 4 or 5 distinct piles. The first one is going to be long bones. And that's exact, and their name describes them exactly. They are longer than they are wide. These generally are found in the appendicular skeleton, although not exclusively. Classic example is the femur. It's the longest part of it's the longest bone in your body, often the strongest bone in your body, the most weight-bearing capable. Your humerus, which is the long bone in your arm, it's your upper arm bone, attaches your elbow to your shoulder, to be very unscientific. Those are great examples of long bones. But if you even think of your thoracic cavity, your ribs are very long in proportion to their width. So long bones are the first category. Second category, if long bones is the first, there are short bones, and they are small, they are thick, so their length is equal to their width. They're a lot more cubic in their proportions. So some great examples of this are your wrist and ankle bones, what are called your carpals and your tarsals, and so respectively. And so, yeah, it's exactly, if you were to sort these into their own pile, they'd be short and stout and square-like. Second, third, oh my goodness. The third are your flat bones. These are thin and flat. These are found in your skull, your sternum, your ribs. I misspoke earlier, my apologies. And your scapula. And a fantastic example is the parietal bone in your skull. And that's the parietal bone right here. And the fourth category is irregular. So if it's not long, if it's not short, and if it's not flat, it's an irregular bone. And basically, this is your vertebrae. Weird shaped things like this that are so intricately shaped with such fit for purpose shape. And as well as your hyoid bone. Total side note, my friend and I have a very long standing joke where every time we see each other, we say, "Good to see you, I'm going to break your hyoid." And I'm not sure how it started, but we're just going to, I don't know, that's a stupid story. Maybe I'll cut that out, maybe I won't. Either way, much more interesting story about hyoids has to do with cats and the sheer fact that the difference between a cat's purr and cute meows is because they have a hardened or, ossified, bona fide hyoid bone that sits right there in their throat, and the vibrations of that hardened, ossified hyoid bone do not make a very loud noise because it doesn't vibrate with the frequency that, say, a cartilaginous hyoid bone would vibrate with in order to make not a soft purr, but a very loud roar, such as in a tiger or a lion. So that simple difference in one being ossified or another leads to different resonance of the two different bones. That leads to very different vocal messages that get sent. One is cute and cuddly, and one is I want to eat you. And then the last classification of bone, and this is a very niche category, are sesamoid bones, and these are very small. They're also very flat, and their key component is that they develop inside tendons or near the joints of the knees and the hands and the feet. And so here we have a medial view, mid-sagittal view, if you would, of the foot, where we actually get a chance to look at some of the sesamoid bones that occur just inferior to the oh my gosh. And here we have a medial foot view, a mid-sagittal view of the foot, where we look at and can see that these sesamoid bones develop within the tendons directly inferior to these metatarsal bones, sort of the phalanges of the foot. And so, yeah, these little bones right here, bing, bing, they develop inside this tendon, which I can't remember the name of that tendon. It's something longus. It's the it's right here. The flexor hallucis longus tendon. Yep. So, yeah, they develop within that tendon in order to help support the base of that foot. And so then now that we've sort of sorted all the bones in the skeleton into their, I think it's 5 different shape categories. If you were to just sort them into different piles, you'd have your long, your short, your flat, your irregular, and your sesamoid. And now we want to look at the skeleton sort of as a whole. And when you do that, you see that there's 2 main compartments. There's the axial portions of the skeleton, or the trunk of the skeleton. And this is basically the body without the skeleton without the appendages, which is the next which is the next section. This includes the skull, the hyoid bone, like we discussed, the vertebral column, and the thoracic cage. Whereas the appendicular portion of the skeleton contains those appendages, the upper limbs, the lower limbs, the pelvis, and this is this can be tricky right here. And we'll get to that in a second. And the pectoral girdle, the scapula, the clavicle, things of that nature. And so now we're going to dive into the different sections of individual bones. And so to do this, to really look at how bones are formed as in general, and to do this, oh my God, I can't do this. And to really look at how bones are formed in general, we tend to look at their internal structure in the context of long bones. Simply put, they're big, they're easy to see with very distinct sections, so that's in general how this is primarily done. And so with long bones, it's very easy to see the different sections of this bone that we're going to go over in these subsequent slides. And again, as much as I wish that I was giving you this lecture in person, we would probably have tried to get our grubby hands on some sort of bone dissection, because at least when I was in high school, I was very fortunate to have an absolute amazing lunatic for a teacher who really, really let us dissect anything and everything. I think we did at least 12 dissections in that class. Either way, one of my favorites was just dissecting different types of bones, and I think we actually dissected a moose femur. And it was just really neat to see the very discrete cavities that you read about in a book. And so, as much as I wish we could do this in person, here we are looking at a delicious bone marrow bone, where you've got your spongy bone up top, which is a really neat sensation as it sort of bleeds down into the marrow cavity down here, and you can see the different types of marrow. But either way. Long bone structure. The first thing, if we're sort of moving from out to in, that we encounter is the epiphyses, plural for epiphysis, which is Latin for, if those Latin roots break down into growing upon. And these are the ends of bones. And usually these articulate with some other bone and form a joint with another bone. And so if we look over here on this diagram, these are the growing upon, these are the ends of the bone. So when we look at these ends of the bones here and here, both in the proximal and distal sections of this femur, of this right femur, we can see that these sections right around here, okay, actually, right around here and right around here are the epiphyses where this bone interacts with other bones. The diaphyses is in between the epiphyses. And so instead of the Latin roots when broken down meaning growing upon, diaphyses mean growing between. And so this is the central shaft of a long bone, and this is where you find the vast majority of the compact bone that we'll get to in just one second. the vast majority of that compact bone is located, whereas the vast majority of the spongy bone is located in these epiphyses, whether it's the proximal or the distal. And at those epiphyses, it's important to mention that we have our articular cartilage. So cartilage that's located at a place where the bone articulates with another bone. And so this is that really, really glossy type of cartilage, particularly the stuff if you've ever eaten chicken wings or something like that. It's the stuff that really doesn't come off of the bone while you're trying to eat it. It's that really dense, really glossy cartilage that covers the ends of bone so that they can have a nice, smooth contact point with the other bones. And spongy bone, like I said before, is the majority of which is usually located in the epiphyses. And so up here we have this speckled hollow sections, and that's where the spongy bone likes to make its home. Spongy bone is less dense than the compact bone, which we'll get to in the next slide. Yes, we will. And this is where the red marrow likes to house itself for that hematopoiesis, as well as all the other types of poieses that happen inside the bones, tend to happen at the proximal heads of the femurs, as well as in a lot of locations inside your hip girdle. Those bones, whether it's the ilium or the ischium. And moving on to the compact bone, which is obviously more compact and thus more dense than spongy bone. It makes up the walls of your diaphyses, and just a reminder that the diaphysis, as opposed to the whether it's the proximal or distal epiphysis, is the section of these long bones that is in the middle, with those epiphyses being on the lateral ends of long bones. So the diaphysis contains the compact bone, whereas the epiphysis contains that spongy bone, which houses that red marrow. And so within this diaphysis, it contributes 80% of the weight to the human skeleton. So the majority of the weight of your skeleton is contributed by these diaphyses. My apologies. And because mainly that's where you find this compact bone right here. And it's a little bit more difficult to see on this image, but you can hack into this presentation and take the image and blow it up. I can also supplant you with other images as well. But if you zoom in here, you can pretty clearly see that the compact bone is way more dense. There's a lot fewer pockets, not air pockets, but pockets for things to be in, as opposed to the spongy bone right up here where the red marrow lives. There's lots of pockets, more sponge-like, as opposed to the compact bone down here. When we move on to yellow marrow, which is again mainly comprised or composed of lipids and ions, ion storage and lipid storage, we find that this is generally housed in the medullary cavity, which is this central cavern running through the middle of the diaphyses of your long bones. And here you can see that going from here to around here, down by the distal portion of this femur. And within that medullary cavity is this stuff, this yellow marrow, that yellowish fatty substance, which is this storehouse of lipids and ions. And like I was saying earlier, the medullary cavity is within the diaphyses between the two epiphyses of a long bone, with that yellow housing that yellow marrow. And if we move on to the periosteum, which if you break down the Latin root words, stands for around the bone. This refers to the fibrous sort of outer sheath that covers the bone and provides the nutrient-rich blood to those bone cells. And you can see that periosteum here. And so when we zoom in and look at the red marrow, like I said before, this is the site where hematopoiesis occurs or blood cell formation happens. Hematopoiesis, again, just to clarify, being only one of the different poieses where all the different constituents of blood cells and all that goes into your blood volume get made. Erythropoiesis being just another example. This happens primarily in flat bones, such as the ribs, the sternum, and most notably the pelvis, and then the diaphyses of your femurs, the biggest long bone in the body. And so now we move on to this section of the presentation. So this next section of the presentation walks you through the different ways and the different things you're going to be responsible for absolutely knowing the location of and how to identify them of both the anterior skeleton, the posterior skeleton, and then the cranial skeleton as well. And so those are the things you're going to be responsible for being able to know the location of and identify visually. And so you'll be responsible for being able to locate the orbit or the eye socket inside of skull. And again, this is for the anterior skeleton. You'll be responsible for being able to locate the mandible, the lower jaw, the sternum, your breastbone, the xiphoid process, which is the pointy bit at the very bottom of the sternum, your costal cartilage, which helps our rib cage expand. It's the cartilaginous portion of that rib cage. The hip bone, or the coxal region, which is the ilium, the ischium, and the pubis by sight in the anterior skeleton. And then most notably being able to certainly identify the ilium, which is the largest bone in the coxal or pelvical region. Here again we have the ilium, which make up those sort of wings, those lateral wings of this hip region, your sacrum being part of the axial skeleton, the rest of it not being part of the axial skeleton, and in fact being part of the appendicular portion of the skeleton. And here again is the ischium, which is the more inferior portion, and specifically the pubis, which is the section of the hip girdle that directly attaches here at the most medial portion that connects one side of the hips to the other. And here the pubis and ischium are listed like I just described. You'll be responsible for locating and identifying the frontal bone or the forehead in the cranial skeleton, the nasal bone, which is your nose, which is the bony portion of your nose, not the cartilaginous portion, the maxilla, the upper jaw, the lower jaw as well, your mandible, which we'll get to in a second, the clavicle, the collarbone, ribs, which are your ribs, your humerus, which is the large arm bone that attaches your elbow to your shoulder, and your vertebral column, which is your spine. You'll also be responsible for identifying your ulna, which is different than the radius. This is one way to remember it. I always like to remember that the radius is your thumb bone. It's the bone that attaches distally, not proximally, to your thumb. And so if you're in the standard anatomical position, which remember is standing straight with your back against a wall and your palms facing out and the back of your hand facing against that wall, your radius is going to be the most lateral portion, the most lateral of your arm bones. And so your ulna is going to be more medial, not on the thumb bone. It's the pinky bone, where your radius is the more lateral of the two and is on the thumb side. Your sacrum, which if we go back, is here and is part of the axial skeleton, part of that main trunk. Your coccyx, which is your tailbone, the carpals, or your wrist bones, your metacarpals, which are your hand bones, which make up sort of the palm section of your hand, and then your phalanges, which are all the digits and bony bits that make up your the most distal regions of your hand, those fingers that are good for grabbing things. Your femur, or your thigh bone, of which there is only one. Your patella, or your kneecap, which again is one of those sesamoid bones, which is one of those bones that develops inside a tendon or ligament sheath. Your tibia and fibula, which are your shin bone and your calf bone, respectively. Your tibia being the most frontal portion. It's actually the one where if you say, oh, I banged my shin, that's because you banged your tibia. It's usually more easily identifiable than your fibula, which is your calf bone and is actually what you perceive to be your lateral ankle bone. So it's that outside bone you feel around your ankle, whereas your medial ankle bone, or the more inside ankle bone, is your tibia, the distal portion of your tibia. Your tarsals are your ankle bones, just like the carpals are your wrist bones, and the metatarsals are the foot bones, just like the metacarpals are your hand bones. And last but not least, phalanges also refers to your toe bones. And now when we get to the posterior skeleton, we're going to see that you're going to be able to identify the parietal side and top of the head. And we'll have a cranial version here. That parietal bone being sort of the sides and, again, the top of your head. Your cervical vertebrae, or your neck, as opposed to your thoracic and your lumbar vertebrae. This is your back, and this is sort of your upper back, and this is your lower back, and this is your neck vertebrae. Your coccyx, which, like we said before, is your tailbone. And in that, again, in this posterior skeleton, you also can identify your femur, which we said before is that thigh bone, your fibula, which is that lateral or outside ankle bone, non-weight bearing, fun fact, and your tibia, which is that medial ankle bone or just your shin bone. The calcaneus is specifically the heel bone in your foot. The occipital bone is the back of the head. Your scapula, or your scapulae, are your two shoulder blade bones. That coxal bone, again, being the entire hip girdle region, which can be further identified as the sacrum, the ischium, and the ilium. And now when we look specifically at the skull anatomy, we're going to be looking to identify the different portions of that skull bone. So primarily the parietal bone, which again is that sort of top and side portion of the skull bones. The temporal bones, which is this orange section here, which is definitely only on the side and contains the bony portion of your ear sections. Right here, we've got the temporal bone in orange again. The occipital lobe, or not the occipital lobe, but the occipital bone, which is the brown section down here, which actually extends into the inferior portion of the skull skeleton and is definitely in the posterior section. That actually, if you reach behind your head and you feel that bump, that's the occipital bone. And the external auditory canal, which is right here. You'll need to be able to identify this frontal bone, which is right here. It's your forehead that extends up until where it connects with the coronal suture to the parietal bone. The sphenoid bone, which is right here, which is directly frontal or ventral to the temporal bone. The nasal bone, which, like we said, is the bone that's associated with your nose as opposed to the cartilage that's associated with your nose. The zygomatic bone, which is if the sphenoid bone is directly ventral or frontal to the temporal bone, and your zygomatic bone, which is the section of bone that is commonly associated with this orbital arch right here, as well as your cheekbones. That's your zygomatic bone. Your maxilla and your mandible make up your chewing apparatuses, which are here. Your maxilla being the upper section, which associates near the bone associated with your nasal bone, and your mandible being the lower section of your chewing bones. Obviously, when you chew up and down, you can feel your mandible moving up and down where your maxilla is stationary, your mandible being the section that actually does the movement for chewing. And that wraps up section 1. So now that we move on to part 2, we are now going to be looking at bone formation, growth, and remodeling. So basically, how do bones grow? How do they harden themselves? And how do they remodel themselves after they're damaged? It's important to start at the beginning, and so when we look in an embryo, we see that the skeleton is in fact not made of bone, but of that hyaline cartilage, one of those different types of cartilage that we originally covered in our types of tissues. And over time, that hyaline cartilage is actually going to be the base that gives rise to more solid structures, bony structures coming to form inside that embryo as it matures outside of the womb. And so as this embryo develops, the cartilage material in the middle of the bones begins actually to be broken down. And as it breaks down, and as that periosteum forms around the cartilage bones, we'll say, and blood supply begins to make its way into that structure, the coupling of that the presence of that blood supply, as well as now the breaking down of that center, actually begins to form the first parts of the bony matrix. So when we zoom into this process, we see that there are these special bone-forming cells called osteoblasts. Remember that that suffix blast, with that prefix osteo meaning bone, with that suffix blast refers to generation or creation. And those osteoblasts, or bone creators, start producing a bony matrix
which is more rigid, more bone-like than cartilage-like, which ends up covering the original material that's actively breaking down in the center of those long bones that are now growing, and ossifying, because ossification is that term that refers to the formation of bone from cartilage. And so soon those long bones are actually going to develop two secondary points of ossification, as opposed to the original just one. And these are located at the two epiphyses. And so when we look at a diagram of this, we see that the primary ossification center is the place where this starts first. And if we move on to this next one, we see that this deteriorating cartilage matrix, which I mentioned before, is that breakdown of that cartilage matrix as it develops. And so that breakdown, plus now the innervation or the bringing of blood supply to that breaking down matrix, allows for those osteoblasts to take root and start creating what's now actually spongy bone in place of that internal cartilage. And as this goes on, down here at the epiphyses of the bones, after the epiphyses develops an epiphyseal blood vessel or a blood supply to that epiphyseal area, we develop the epiphyseal plate cartilage, which is this active site of bone growth. And we're going to dive into that in just a few slides. And here's an actual scan or a cross-section of those different portions of the long bone and where the growth is occurring. And so the epiphyseal plate is that location in a long bone where the primary growth area is located. And so you have osteoblasts here constantly ossifying and creating bony structures that actually push inward towards the center of the bone to not just ossify it, but also increase its growth. And so this is really a repetition of what I just described, which is that as a long bone grows in length, that band of cartilage near the neck of each end of the bone, called that epiphyseal plate, so this plate that you see here in this distal region of the tibia and the distal region of the fibia, that epiphyseal plate lies in the epiphyses, or the ends of long bones, with the diaphyses being the bits in between the two epiphyses on either end. And so from these epiphyseal plates in the epiphyses, they send out new cells toward the middle, or the diaphysis of that long bone, to not just enlarge, but to also form that bone matrix. So in two ways, it's both growing the bone as well as maturing the bone or ossifying the bone. And it's important to note that bone growth ends during adolescence when these structures are completely ossified. Once they're ossified, once the growth is complete and the ossification is complete, from then on the bones no longer grow, but that doesn't mean that they're now inactive. And contrary to that, it actually means that from then on, all that energy that was going towards growing during adolescence simply means that the bulk of that energy can go towards maintenance and adapting to the different load demands that you put on your skeleton. But during this time up until adolescence, it is important to note that bone growth is primarily controlled by both growth hormones as well as sex hormones. There are a couple other signaling molecules and maintenance molecules that are responsible for the activity of bone both growing and ossifying, but the bulk of that activity is controlled by those critical sex hormones as well as those generalized growth hormones there. And they're the ones that really enact the different steps of these processes. And so when they happen, how they happen, those hormones are what dictate when and how they occur. And so here we actually have a very interesting scenario where this is actually a baby cat skeleton, actually an embryo that I believe is 40 days old. And what they've done is they've taken this embryo and they've stained the skeletal tissue, or at this point the cartilaginous tissue, with two different types of stain. One that binds to cartilage, and that's the lighter blue sections, and then one stain that binds to calcified sections. And this can be seen in the darker red or sort of deep violet sections in those bones. And here you can clearly see where the primary calcification centers are. And specifically, if we look at the long bone, since that's what we're really zoning in on, if we take a look here at the femur, we see that the primary centers of calcification and ossification aren't happening at the epiphyseal ends of the bone. Instead, it's happening right in the middle of the inside the diaphysis of that bone. Just further supporting that when bones grow, they grow from the middle. And so those cells are sent to the middle to both grow as well as both ossify and harden from their cartilaginous state. And now we get into factors that affect bone growth and development. And we're going to look at three primary things. Number one is going to be anything that is damage to the epiphyseal plate, that growth plate. So once you get past a certain stage of development, no longer are you simply breaking down that center cartilage section and filling it in with bone. Now you've got this secondary center of ossification down here at the epiphyseal regions on that epiphyseal line, that epiphyseal plate, where bone is now being sent from there, from that epiphyseal region towards the diaphyseal region in sort of that out to in direction. And so those epiphyseal regions can be seen here on the tibia, here on the fibula, and this is a different view of the tibia and fibula right there. And so any injury that would perhaps damage that epiphyseal line or that epiphyseal plate would in fact hinder the growth moving forward of that long bone. For example, if you suddenly just had a break and or you broke your bone and it actually broke through that epiphyseal plate, you would see that that bone would stop growing at an equal rate to the rest of the long bones that are around the body. And so you might have perhaps some hip dysplasia, not hip dysplasia, but some hip offset where one of your, let's say you broke the epiphyseal plate of your femur, you would have one leg significantly longer than the other that would probably give hip and then back issues. The same scenario could be seen if you did the same thing to right here, your tibia. If we just drew a line here as pretending that there was some sort of pretty catastrophic break down that far on the ankle, if you were unlucky enough to break your ankle in that region, you would see that this tibia, which is a medial view of the right tibia, if you broke through that epiphyseal plate on the right tibia, your right leg would be significantly shorter than your left leg, and you'd likely have a gait that was offset and caused, again, hip or back problems. And this can be seen in any other of your long bones. The other important factor that dictates or has a significant effect on growth and development is adequate vitamin D and calcium in your diet. Now, this is super important because, like we've said before, your bones are a storehouse for minerals. It's a storehouse for minerals, and a lot of times that storehouse is used to help buffer your blood, as well as several other biochemical functions. But primarily, the vitamin D and calcium in your bones is there to help ossify, to help harden, to help strengthen the internal structure of your bones so that your body is ready to cope with the mechanical stresses that you put on your skeleton. And so having vitamin D and calcium in your diet are super, super important for the health of your overall skeleton. And then last but not least, the biggest factor that influences your growth and development of your skeleton to be healthy for your entire life is adequate exercise. And so this represents a very significant factor in that overall health because your skeleton, like I mentioned earlier, does not, once you end adolescence and your skeleton is done growing, your skeleton does not stop being metabolically active. Instead, all that energy that once went to growth now goes to tweaking the ossification of different sections of your skeleton so that it can be ready and prepared for the different mechanical stresses you put on it. And so adequate exercise is important because it actually puts stress or strain on your skeleton in specific certain ways. Take lifting weights, for example. That's putting a tremendous amount of load on very specific sections of your skeleton. And so what actually happens is that your skeleton, still being very metabolically active, responds and hardens and ossifies and re-strengthens the areas that are affected by that mechanical strain so that in the future, if you encounter that mechanical strain again, your skeleton is more able, more ready to cope with those stresses and less likely to lead to some sort of fracture, etc., etc.